Hello, everyone. My name is Fuheng Zhao. I'm a PhD student from UC Santa Barbara. Today, I'm going to present our work, KL plus minus, approximate quantile sketches over dynamic datasets. This work was done in collaboration with Sujaya, Ryan, Professor Agrawal, and Professor Abbadi. Quantile is an important statistical measurement. 0.5 quantile, also known as a median, is very robust. The generalization of median leads to different quantiles. Quantile is a fundamental technique for data analysis, and it is often used to summarize data distributions. Some of the applications include financial services, value range database partitioning, and monitoring network and database activities. Let's first define what rank and quantiles are. Rank of an item X is the total number of items that are less or equal to X. Quantile Q returns an item X such that the rank of X is equal to Q times the total number of items in the dataset. In this example, rank of 2 is 5, and quantile of 0.5 is 2, since 2 is a median. Imagine we want to summarize a very large dataset that is being updated very frequently with inserts and deletes. We desire a one-pass algorithm that can process each item exactly once and output accurate statistical information. In 1980, Monroe and Patterson showed that to compute the true median in one pass requires linear space. But how about approximation? With the requirements of using sublinear space, providing tunable guarantee, and one pass of all operations, can we approximate the quantiles with high confidence? In this example, can we say rank of 2 is about 3? Median is approximately 10. Through the past 3 decades of research, several algorithms have been proposed and operate in different models. In the insertion-only model, the input only consists of insertions. Some of the famous sketches operate in the insertion-only model are GK sketch, QDigest, and KLL. In the turnstile model, the inputs consist of both insertions and deletions, where deletions were previously inserted. Some of the well-known sketches operate in the turnstile model are range subset sum, dietic count mean, and dietic count sketch. Recently, an intermediate model, the bounded deletion model, was proposed, such that the number of deletions is bounded by 1 minus 1 over alpha number of insertions. By setting alpha to 1, 1 minus 1 over alpha becomes 0. Hence, the model becomes insertion only. Our proposed KL plus minus operates in the bounded deletion model. The basic structure is an array of buffers. Each buffer has level, capacity, and weight, where capacity and weight are determined by level. Initially, there's only one level with capacity of K. After processing K inputs, the buffer becomes full and leads to a compaction. The full buffer will be sorted and half of the elements will be pushed to the higher level buffer with doubled weight. In this example, a new buffer needs to be created. The topmost buffer always has capacity of K, and each lower level decreases capacity by a constant factor of C, where C is in between 0.5 and 1. This data structure is used in many well-known algorithms. To support deletions, we proposed the conditional compaction process. Our previous compactions are sort the buffer and then push half of the elements. In KL plus minus, we buffer the deletes. The conditional compaction process is, we first sort the buffer. If there are any delete insert pairs, we discard them and return. Otherwise, we push half of the elements. The return after discard operation is crucial. Discard operation does not introduce any rank error and will create new free spaces. Return after discard will ensure the push operation is performed on a full buffer. So here's an example. Item 1 to 8 are inserted, and then items 7, 3, 2, and 1 are deleted. After processing the first 6 insertions, level 0 buffer becomes full and needs to undergo a compaction. After the compaction, items in the even indices are being pushed to level 1 buffer. Level 0 buffer decreases its capacity to 4, and after storing the next 4 items, it becomes full again. In the next compaction, we can see there is a matching -7 and 7. So they can be discarded, which created 2 more new free spaces to -2 and -1. The last compaction will push -2 to level 1 buffer, and note -1 and 8 are now being pushed since they are different operations. After processing all operations, the true data sets contain 4, 5, 6, and 8, and our estimation is -1, 2 4s, 2 6, and 1 8. The true rank for item 5 is 2, where in our estimated rank it is 1, so it is off by 1. For the rank of other items 4, 6, and 8, we accurately approximate their rank. So what are some benefits in operating in the bounded deletion model? One important benefit is that KL plus minus does not rely on the assumption of a bounded universe and leads to a smaller space bound and faster update time compared to sketches in the turnstile model. Each compaction may introduce plus minus W with 0 rank arrow for buffer with weight of W. By pushing even indices or all indices randomly, the expected rank becomes 0. Since the expected rank arrow is 0, we can bound the total arrow with Hohen's inequality, and hence it leads to a smaller space bound, which is independent of the universe size. We also showcase an algorithm for fixed size sliding window quantile approximation, where new items are inserted and outdated items are deleted. In this video, the window size is 1000. The input is sorted random integers from range 1 to 5000, and the sketch space is 64. The blue dots are approximations, and the yellow line is a true distribution. We can see the approximation is quite accurate. One might be curious about why there are few blue dots at the very beginning. Those are the traces left out by deletions. So for more details, it is described in the paper. Some experiment highlighted with more insertions leads to less accuracy. But we can increase the sketch space to tolerate those deletions. Essentially, increasing space leads to better accuracy across all different data distributions. And note, with 90% of deletions, KL plus minus still has more accurate estimation compared to the state-of-the-art data count sketch, when both sketches use the same space. In summary, we present the first randomized quantile sketch KL plus minus in the bounded deletion model. We showcase how to reduce update time in KL plus minus by incorporating an optimization strategy from a previous algorithm. We apply KL plus minus sketches to maintain approximate quantile estimation in the fixed sliding window over datasets. Thanks for listening to my talks.